good evening, everybody. I think you can hear me fine. So my talk will be about tropospheric delays and tropospheric delay modeling. Let me. Okay. Well, strictly speaking, we should not talk about tropospheric delay, but it is actually about delays in the neutral atmosphere, because we not only have to consider the lower 12 or so kilometers, but actually we have to consider layers up to about 100 kilometers. In important terms for us are refractivity and refractive index. And these two quantities, capital N and small n, can be calculated from pressure, temperature, and humidity. And we have to keep in mind that we typically separate the total refractivity into two parts, which is the hydrostatic part and the non-hydrostatic part. And the non-hydrostatic part is often called wet refractivity. But now let us first define the tropospheric delay. So what is actually the tropospheric delay? And in order to do so, we have to calculate first the electric path length, capital L. So this is the equation for the electric path length, meaning that actually we have to integrate over the refractive index along the bent ray path. So this is the shortest in time reaching our GNSS station first. So here we do have the satellite, and here we do have the GNSS station. So this is the electric path length. And the tropospheric delay is actually the difference between the electric path length and the geometrical distance between the station and the satellite. So this difference here is the tropospheric delay. And well, we can separate this again into hydrostatic part and the wet part. So we do have the path delays along the bends line, plus we also have to consider the so-called geometric bending effect. So that's just a geometric distance here, S, and the straight line G here. So this bending effect, S minus G, this is approximately 2 decimeters at 5 degrees elevation. And there is no need to worry, we do not forget about this, but actually it is part of the hydrostatic mapping function. Okay, so that's the tropospheric delay. And I would like to take a look at the refractivity with height. So this plot depicts the refractivity from radial sun data. So from radial sun data, we get pressure, temperature, and humidity, and we can calculate the refractivity. And actually here we already do the separation into the hydrostatic part here and into the wet part. And we plot here the hydrostatic refractivity with height in blue and the red refractivity in red. And so it's pretty obvious the behavior of the hydrostatic refractivity with height. This is very smooth. And essentially, the hydrostatic refractivity can be calculated from the total density. So this behavior is smooth, and you can think that if you integrate over the density, you get the mass, and you can, with the gravity, you can connect. Sorry. So you can connect the mass to the pressure value. So actually, the pressure value at the site is a very convenient quantity to characterize the hydrostatic part above you. So that's for the hydrostatic part. On the other hand, this is not true for the wet part, because if you know the water vapor pressure, you do not know the vertical behavior of the wet refractivity. So that's a big difference between those two quantities. So actually, this will provide some possibilities for the hydrostatic part, and you are probably familiar with the equation by Sastermoinen, which goes back to 1972. And actually, this is a very convenient tool to determine the hydrostatic zenith delay from essentially the pressure at the site. So this function F is very close to 1. So if the pressure is 1000 hectopascal, the hydrostatic zenith delay is approximately 2.3 meters or 8 nanoseconds for a station at sea level. So in order to be able to calculate the hydrostatic zenith delay, we need the pressure. So the best possibility is, the best choice is to use pressure recordings at the site. But sometimes these pressure measurements are not available. Then you could try to get pressure values from numerical weather models, for example, as they are provided with the Vienna mapping functions, or there are, of course, also other providers for these pressure values. And if you're not able to access these pressure values, you have to use some empirical or blind models like GPT-2, or there are several other models by various institutions. So, but you should keep in mind, so this is a caveat. So if you use such a blind or climatological model, you should not use atmosphere loading corrections, because actually when you use such a climatological model, you implicitly do some kind of atmosphere loading correction. So if you use GPT-2 to generate the station coordinate time series, then you should not use this time series to look for atmosphere loading, for example. Okay. So how do we do troposphere delay modeling then? So here, delta L, this is the tropospheric delay. And so we take pressure values at the site and we calculate the hydrostatic zenith delay. Then we take the hydrostatic mapping function to map the hydrostatic zenith delay down to lower elevation angles. And we estimate the wet zenith delay with the wet mapping function as partial derivative. So this zenith wet delay in global cases, global applications, this is estimated as an unknown parameter. Typically, zenith wet delays per station are estimated every 20 to 60 minutes, and you could use some piecewise linear functions, piecewise linear offset functions, and so you could calculate or estimate the zenith wet delays like illustrated here. Okay. So we need mapping functions, and now we have to be careful because we not just estimate wet zenith delays or zenith delays in general, but we typically also estimate station heights and station clocks, as we heard before. And there are different partials for these three parameters. For the station height, it's exactly sinus elevation. For the clocks, it's exactly 1. And for the zenith delay, it's the mapping function. But the mapping function is not perfectly known, in particular at low elevation angles. On the other hand, low elevation observations are necessary to decorrelate heights, clocks, and zenith delays. So that's a bit tricky. And this also means that our mapping function errors show up, for example, as station height errors. So we need very good mapping functions to avoid station height errors and clock errors also. So we have to look for best possible cutoff elevation angles for our observations. For example, we could use 5 degrees or 7 degrees or 10, perhaps combined with an appropriate down weighting scheme. Okay, but I would like to illustrate a bit more what actually happens when the mapping function is wrong. So let's take a look at this figure here. Here I did plot the VLBI radio telescope, but this can also, of course, be a GNSS antenna. In blue, we have the perfect situation. So we do have a tropospheric slant delay, that's this, and we do have a zenith delay in blue, and we do have a perfect mapping function which maps down the blue zenith delay to the blue slant delay. So that's the perfect situation. But now if we assume that our mapping function is wrong, our mapping function is too large. So if our mapping function is too large, on the other hand, the observed tropospheric delay stays the same. This means that the zenith delay decreases. The zenith delay decreases, and consequently the station height goes up. So if our mapping function is too large, the station height is also too large, and the zenith delay is too small. Actually, it's not a one-to-one correlation between station height and zenith delay, but if the change in station height is 6 millimeters, the change in zenith delay is minus 3 millimeters approximately, so just half of the station height change. Okay, so that's the consequence of a wrong mapping function. But actually, how do those mapping functions look like? And we typically usually use the continued fraction form, which was introduced like this by Tom Herring. And essentially, we do have three coefficients, A, B, and C. And when we now, for example, take a look at the Vienna mapping functions, with the Vienna mapping functions, we use empirical coefficients B and C, meaning that those coefficients are calculated from latitude, longitude, and day of year. And just the coefficient A is determined from ray tracing through numerical weather models. So when the Vienna mapping function is provided, actually these coefficients A are provided on a global grid or for specific sites like all IGS sites. Okay, so well, the Vienna mapping function is probably a recommended one, but you need access to the A coefficients, and if you do not have access to the A coefficients, then you again have to take some kind of blind or empirical mapping function. For example, the global mapping function, again, there are more possibilities. And the global mapping function, for example, is a kind of averaged Vienna mapping function. So how does this look like? This plot depicts the hydrostatic mapping function at 5 degrees elevation for a station in Brazil at 5 degrees elevation. And in gray, we see the Vienna mapping function, and in red, the global mapping function. And we can assume that the Vienna mapping function is more accurate than the global mapping function. And of course, this difference, this generates station height biases. So you could use a rule of thumb to calculate the impact on the station height. Okay. And well, when you do GNSS analysis, you typically not only estimate zenith wet delays, but you also estimate tropospheric gradients. So actually our tropospheric delays are not just dependent on the elevation angle, but also on the azimuth A. And this is considered by using a north gradient and an east gradient and a gradients mapping function. So this is the symmetric part here. So we typically estimate the north and east gradients, for example, every 3 hours or every 6 hours. And their size is approximately 1 millimeter. But if this parameter here is 1 millimeter, this essentially means that, for example, at 5 degrees elevation, that's an extra path delay of about a decimeter. So, and why do we need tropospheric gradients? Because we do have to consider for the atmospheric bulge, as illustrated here on this figure, or we do have coastal situations and in general various weather fronts where we do have different delays in different azimuth angles. Okay, and finally I have 2 slides with comments on regional and local networks, because in those situations it's a bit different. In regional or local network solutions, the tropospheric parameters may get correlated to the satellite clock parameters, so they cannot be solved in an absolute sense. So in that case, you may estimate tropospheric parameters for all but one station. So you have to fix the troposphere delays for one station, or alternatively, you may introduce troposphere estimates from an external, preferably global solution. And finally, in case of real local network solutions, there is even 100% correlation of the troposphere between the stations. And so if all receivers are located at the same station height, so you don't need to estimate any tropospheric parameters, but if you have a height difference between the stations, then a troposphere bias has to be considered or should be estimated. Okay, so that's it. Thanks for your attention.
Thank you, Johannes, for this presentation. Are there questions to Johannes already now before you have to write an email?
Well, yeah. So
if not, I have.
Okay. No.
I have one to you.
Mm-hmm.
We know that you are producing coefficients for the Vienna mapping function, but there are also other sources from Canada, GFZ. What is your recommendation if for some reasons your server is not reachable, but I'm in hurry to submit my solution in time?
Mm-hmm. So I did not do comparisons and tests myself, but I certainly would recommend you to use the GFZ coefficients or other parameters. Yes. Mm-hmm.
Okay, they are also based on the ECMWF like yours, or why?
I think so with the GFZ, yes. And the good thing is that they are using the same concept also with the A coefficient. Okay. So that's quite convenient to replace one by the other, but I definitely recommend using those. Mm-hmm.
Okay. And more, you prefer then GFZ instead of switching to the GPT GMF?
Yes, I certainly the Vienna mapping function type, these are more accurate, so the metrological are more accurate than the blind ones. Mm-hmm.
Okay, thank you. Are there other questions? It's already too late in Europe, I see. Okay, then thank you, Johannes.